Thank you. Thanks a lot. So first of all, thanks a lot for inviting me to the workshop, and to new students and participants, welcome. I hope you will have a time in this course and this activity that gives you actually an outcome. And thanks a lot also to Catherine. Congratulations, Katarina. Congratulations with your work. And I think you gave a very brief, excellent presentation of the opportunities and some of the challenges related to the plastic system in managing that. So I'm Professor of Industrial Ecology at the Norwegian University of Science and Technology. I will give a presentation. So it was introduced as sustainability concepts and applicability to plastics waste. I'm not going to talk too much of sustainability without putting it in context to plastic waste and to the plastic system, because I think most of you have already learned about sustainability and more in a generic way. So let's just get starting. When we think of sustainability in general, of course, we know that it's about protecting the earth and our lesser society. We think of going back to the Brundtland Commission, developing and initiating the Sustainable Development term back in 1987. So obviously combining a future development in society so that you are both protecting societal, economic and environmental concerns. However, now we also have the UN Agenda 2030 items to relate to the 17 SDGs, Sustainable Development Goals. And of course, what is important, since they are so wide and they are also interconnected and they can be applied to any kind of system or activity in society, and actually they are being done so at the moment. How do they relate to plastic waste and ocean waste pollution problems? And of course, you could just pick some of these and say aspects of plastics and the use of plastics and the benefits of use of plastics to society will most likely interfere with several of these SDGs. And for instance, when I'm thinking of the fact that plastics actually do serve as function in society, it's not just a waste problem, that's after it's discarded, but it serves a function. So that means it's tightly related to value creation. And value creation, of course, that is about jobs, good economics. It's about the industry activity, the infrastructure that we have in society. So obviously you're pointing directly to SDG number 8 and 9. And also it's related to responsible production and consumption and circular economy that Katarina introduced. So that will be SDG 12. And the problems related to the mismanagement of plastic systems, create pollution and environmental impact. So then we are back to problems related to water, if it's on land or sea, ocean water systems, SDG 6, and obviously related also to climate change and to life on land and life below water. So you see, there are so many connection points, and if you go down to the lower level of the SDGs, to the criteria, of course, then you can see physical examples of that. And another very important relationship between the SDGs is that very often we think of them, we hear that they are connected, but we think of them as being goals in parallel. However, they are not goals in parallel in reality, because they are so strongly interconnected and they are depending on actually the natural basis. So the biosphere is kind of the supporting foundation where society and economic may grow and may exist within. And therefore, some people say that the SDGs, sorry, number 6, 13, 14, and 15 related to biosphere is more underlying important than the other ones. This message has been advocated, for instance, by the Stockholm Resilience Center. And that means, of course, that any kind of long-term plastic waste management strategy should focus on the environmental impacts. of course, and solving the economic and the societal both opportunities and the challenges related to the plastic cycle within the capacity of the biosphere. So, and therefore, the whole problem gets quite complex, and it's simply just no straight answer and short fix to the challenges that we see today. My profession is industrial ecology, and I regard it as a subset of sustainability science, or a branch of sustainability science. The field is inspired from ecology. And what do ecologists do? Well, they examine and understand processes and behavior and competition and evolvement and so on in nature. Cyclic behavior of substances and nutrients, the food web and so on, for instance, in natural ecosystems, is some of the things that ecologists study. So an industrial ecologist would take the inspiration from ecology and apply that to the society, to the technosphere, so to speak, and with the technosphere linked to the human to the human preferences and the actors we have in society. So therefore, the diagram on the right-hand side here shows that there is a flow of products extracted on the basis of raw materials and so on from nature to consumers. This is the life cycle, and then when the different items that we are using are discarded, they become waste, we recycle them, or we reuse them, or we will try to handle and process the waste so that it has a safe disposal. And there is, of course, more and more efforts on the secondary production, so trying to recover the resources that are valuable, economically or physically valuable, or biologically valuable, and let them be used again as byproducts, not as waste, but as valuable byproducts back into new production. So kind of the secondary loop will be here. So the industrial ecologist, very often, as let's say, as a scientist, we say that it's our job to understand these flows and these conversions. So what I call the metabolism of production and consumption systems and their environmental impacts. We don't so much examine the social and the economic impacts, but we do focus on the environmental impacts of these flows and conversion processes at different scales. And that means that we have to understand what are the value chains, what do they look like, what kind of actors and companies and agencies are involved directly in the handling and processing, or indirectly, including industries, including, let's say, supporting schemes and so on. We also need to examine and know what are the technologies that are used in the different stages of the life cycle or the value chains, and how each of these technologies actually consume utilities, generate emissions, and so on. And when aggregating this together, we can understand kind of the system-wide character of the secondary, of the primary and secondary production systems and their environmental implications. And of course, we use quite a few of the methods in order to understand these questions. There are analytical methods and there are procedural or management related methods. So the analytical methods that we are using, very often you see references to that in sustainability literature. And basically it comes mainly from the field of industrial ecology. It is life cycle assessment. The task in life cycle assessment is to examine the potential environmental impacts on air, on water, and on land related to a product over the product's life cycle, full life cycle. And the product could be a conventional product like a washing machine, or it could be a service like a streaming service for music. Any kind of product and services have a life cycle. So regardless of where that production or activity physically takes place, with, for instance, raw material extraction in Brazil, with the manufacturing of the products that are to be, in the end, to become a washing machine. Maybe some of the parts are produced, are manufactured in Taiwan or in Japan, and with a final assembly of the washing machine, maybe that takes place in the Netherlands, and the washing machine is used in Norway and discarded, and the waste becomes entering the waste system in Norway. So regardless of where it takes place, we use life cycle assessment, or LCA, in order to understand the environmental potential impacts: climate change, acidification, eutrophication, ecotoxicity, and so on. You have also heard of, I guess, methods like the carbon footprint. So very often we read and we hear in media that the carbon footprint is this and this large. This is actually the sum of carbon dioxide emissions throughout the life cycle. So it's one aspect of what is the different environmental impacts that is examined in LCA. However, carbon footprint is quantitatively, analytically measured in another way. So when you examine life cycle assessment, you look at the technologies that are used and the quantities of that, or dimensions of that technology at any kind of the system, given one, let's say, functional unit. For instance, 1 ton of or one washing machine, or 1 ton of paper that is produced. However, when you look at the carbon footprint, you work with more macro scale solutions coming from econometrics. So in econometrics, modern societies are very well characterized and quantified today with respect to what is the economic activity of different sectors in society, in order to provide you and me with the services and the products that we consume during, for instance, 1 year. So you have a purchasing profile and I have a purchasing profile, and we can say that, well, take certain sectors of that, transportation services, or the services of washing, the services of residence, of residing, and so on. And we can break that down, and we can link environmental impact, environmental emission data per sector to the econometrics, to the monetary data. And that means that we can calculate or estimate basically what will be the carbon footprint or the water footprint, all the kind of footprints. So these two methods, the life cycle assessment and the carbon footprint, or other, let's say, footprint methods, they are complementary. And they're also quite standardized in the way they are done. And that means that we can use those methods to examine any kind of system: electric vehicles, in relationship on comparison to conventional vehicles, power systems, waste treatment, shipping, buildings, and so on. And therefore, what is super important in sustainability sciences today is to try to understand how do different small measures add up to large impact transitions. So at the different scales, from the micro and the meso scale to the macro scale in society. And certainly that holds for the transition of, let's say, buildings in cities, the transitions to more use of renewable energy in the power systems and so on, when we know that we need to be low carbon or basically zero carbon in terms of the power systems in 2050, and certainly in waste management. And plastic waste is obviously one of the problems there. So I will spend some time on informing you about some aspects of plastic waste management in Norway. Of course, the plastic waste situation and the problem is kind of different in every country. So the countries where you come from as participants to this workshop, you might have a fairly different look at it. But also there are some commonalities, certainly on the challenges and on the technologies, even though the cultural and the economic and the technological systems that are applied are different. So sorry for this slide being in Norwegian, but it says, number of tons of plastic waste managed in Norway, and this was 2017 data. So 44% were materials recycled, close to 53% was converted to with energy recovery, and that covered together more than 97% of the waste. So less than 3% of the plastic waste in Norway were disposed of without materials recycling and energy recovery. So the data looks quite good, right? Quite good data. However, despite that, from time to time we see, media attention to there are problems. So this was in October 2018, so roughly 3 years ago. Suddenly there was on Norwegian media, on national TV, focusing on the failing plastic waste system and market. So some of the hard plastics it was not possible to have it entering the recycling schemes. So only during the summer of 2018, there was in the northern part of Norway 4,000 cubic meters of, let's call it, problematic plastic waste were just piling up, and they had to kind of, should we incinerate it or should we just bury it? They couldn't really incinerate it instantly, so it was kind of a storage, intermediate storage. And this question was, what is the reason for that? This is kind of the plastics nobody wants, and we are about to drown in that kind of plastics. And when you look at other countries and see what is going on in the waste dumps of cities in Asia, you see the shores of Africa, you see the rivers, you see the plastic pitches and so on floating around in the Pacific Ocean. Of course, there are huge problems there. The plastics nobody wants, despite the fact that in an advanced and economically strong country like Norway, where we should have technologies, we do not have the solutions for all the plastics. So there is some underlying problems or challenges. Obviously, you have the waste hierarchy saying that you should prefer prevention over reduction, recycling, energy recovery, and disposal. To what extent is that applied to the plastic systems and the plastics value chain? Of course, you are focusing on prevention, on, let's say, packaging optimization. You cannot just minimize the use of plastics in packaging, because the plastics have a function. It's protecting the product, for instance, in food, from the production, from the factories to the households. But you can do some on it. And reduction, there is of course possibilities to do some, but basically to succeed on prevention and reduction means that we have to change quite a lot of our lifestyles and the way we operate, the way we use products and store products and the logistics and so on. Because remember, the plastics do have a function out there. And that means that a lot of attention should be directed towards shifting away from disposal sites to energy recovery and to recycling. And the problem is that the plastics is such a complex materials that is difficult to recycle. So the circular economy is a principle which is now fully accepted, and in at least in Northern Europe, there is a lot of attention to circular economy, and circular economy and climate change is actually two of the cornerstones now also of the European Union policy. But why is it so difficult then to achieve these principles, to achieve prevention and reduction, so the higher preferred concepts in the hierarchy, and to achieve the large-scale recyclability of plastics, so that we can say that we have a circular economy? Well, I will give you some insights later. Some basic questions. So when I look at the plastics from one just trivial day in my own households, within this plastic bag there is different kinds of plastic bottles and foil and so on. Some of the questions that might be important here for myself is, what is the relationship within the plastic waste generation and management and the economic growth in my country? Because we do see a steadily growth in plastic waste. And why is it so? Of course, my country is in a state where the economy is still growing. There is more and more economic activity, and that means that the households also consume more products. And with all consumption, actually, there are plastics related, different kinds of plastics. So one relationship for sure is that the quantities of plastic waste from households in a country like Norway is likely to grow also in the future. And since it's so difficult then to prevent it, could we do something about it? Should all the plastics produced come from renewable sources? We hear about there is bioplastics being entered into the market. Should all of the plastic be bioplastics, or should all plastics be made of biodegradable or recyclable polymers? Is it okay that some of the plastics is still fossil if it's fully recyclable? And if you are in countries actually where you have a well-developed infrastructure for take-back systems and recycling, which, for instance, we see in Norway. So these are some basic questions that is difficult to answer, but that I have been asking myself over the last years. So the challenge of recycling, when I look at the literature, this was a quite nice article and a nice figure. You see the reference down here. There is one underlying challenge, and that is that there are so many different polymers and types of plastics involved. Globally, 18% of the plastics is recycled, up from nearly zero in 1980. And you see here there is polyethylene, PET, terephthalate, beverage bottles, clothing and carpet fibers, some shampoo bottles, and so on. There is high-density polyethylene. There is PVC, polyvinyl chloride, which you can, for instance, have in door frames, in pipes and fittings, and so on. There is low-density polyethylene, polypropylene, polystyrene, and many others. And when you look at these different plastic types, of course, one of the very important questions is, to what extent is each of these types recyclable, given the recycling technologies that we have access to today, that exist today? And to what extent are these different plastic types biodegradable? So let's look on the recyclability. There is some warning signs here. If you are blue, green, number 1 or 2, it's fairly easy. So PET and HDPE is fairly easy, straightforward. And this one, 4 and 5, is manageable. They can be recycled with slight difficulties. However, the red is difficult and the dark red is very difficult. So it means that polystyrene, PVC, and many other plastic types are very difficult to recycle. And that means that, first of all, you have several plastic types at large quantities. So PVC, that's only 5%, and polystyrene 6%, but the others is 24%. And these that is manageable sum up to 39%. So it means that large shares of the plastic, let's say, waste that is generated every year, there are large shares of that is not straightforward to recycle from, let's say, chemical reasons, plastic composition reasons, given the technologies that we have today. And the second challenge, of course, is that these plastic types are mixed in the plastic, let's say, flow. When you collect plastics in a city, you have all these mixed. So how can you then think of forwarding that flow of plastic waste into one, let's say, recycling scheme? Obviously, you would have to separate them, right? So we did a master thesis. So one of my students a couple of years ago, so Irmelin de Sardaler, she looked at the city of Trondheim, and the question was quite straightforward. Would it be possible, by use of industrial ecology analytical methods like material flow analysis and life cycle assessment, to try to understand what happens with the plastic waste that is collected in Trondheim with the aim to be recycled. And Trondheim has a city of some 200,000 inhabitants. There is around 40,000 students, so it's a quite young and lively city. However, it's fairly representative of Norwegian cities and therefore also cities in Scandinavia. And we were looking also then to scenarios towards 2030 with the reference system as it is in 2017. And then looking at what might happen if you are introducing new central sorting facilities, and then if you are gradually phasing in bioplastics in the use and consumption of plastics in a city like Trondheim. So I don't have the time to go into the details of this, but we can upload the thesis so you can read it if you have interest. But first of all, when doing a material flow analysis, you have to quantify, understand where does the plastics go. So there is a system drawing. These are the households in Trondheim. So waste is collected, and the plastic waste was collected in Trondheim partly with the source separation. Some of the plastic in the city, and the residual plastic, the residual waste intended to not contain so much plastics were sent to an incineration facility. Of course, there were also some plastics wrongly thrown in these bins and ending up here. So the system, there is a green system boundary here, and that is actually the system, the activities that is controlled and owned by waste and the waste management facilities and company in Trondheim. The incineration facility that is owned by the end. And then after the waste is packed, it's shipped to Germany, because in Germany there are 5-6 more advanced recycling facilities that has the capacity of transforming these incoming plastic wastes to a product actually that has a good enough quality and price that it could be sold on the market and be used again as a secondary product, substituting virgin materials. So meaning this is real recycling. And also some plastics were exported to Asia with the intention to also have some of that successfully recycled into new products, substituting virgin materials here. So much of the activity happens far away from Trondheim. What can then I do? Well, I can, as a member of a household, focus on as good as possible sorting my plastics in the correct way. And what could the system do? Well, the system could try to have as pure fractions as possible and as good handling as possible, so that in the end, as much as possible could end up here in the blue dots of what I generate in the start at the red dot. So the recycling efficiency means that if there is a good recycling efficiency here, as much as possible would end up here. So I could take the quantities per year, tons per year, being actually recycled from Germany or recycled from Asia, and divide it by the inflow quantity, and that would give me the recycling efficiency. So what do you think? How large do you think it is? Well, honestly, it was disappointingly low. So in 2017, even in a country like Norway, with a good economy, with developed systems, the recycling rate was down to 13%. And if Trondheim, who does not have a central sorting facility, would implement such a sorting facility, this would increase to some 30%, or with ideal, theoretically, central sorting, maybe up to 67%. So that points to the fact that there are several difficulties in the system and barriers towards, let's say, a very high recycling rate and a very good performance of how the system is to be functioning in order to actually achieve a circular economy. So this is a central sorting facility demonstrated at the facility of Roaf, just outside Oslo. I thought I would like to show you that. So let me stop sharing this one. And I can share, share the other file, just a minute. So, whoa, that, hopefully it works. This tells you about the Roaf facility.
The inhabitants' household and food waste are collected by ROAF on a regular basis. The waste trucks arrive and the waste is fed onto the conveyor. The conveyor delivers the waste into the sorting plant. In the sorting plant, the green bags of food waste are being sorted out first. Sensor technology from the Norwegian company Tomra Sorting, Titech, makes spectrometric readings by using near-infrared, NIR, light, which reads the type of material and its quality. The waste bags pass through a bag opener, then drum screens, and the vibration screen will separate the waste according to sizes. NIR technology sorts waste with the right size into 5 types of plastic, mixed paper, and residual waste. Highly skilled employees are monitoring the machines constantly. The plant is fully automatic and one of the most modern waste sorting plants in Europe. Magnetic metal is being sorted out by overband magnets, and an eddy current machine is sorting out non-magnetic metal. A ballistic separator separates the foil from other rolling plastic material. NIR technology separates the plastic into PET, PP, PE, and mixed plastic. The sorting plant will automatically sort out about 2,500 tons of plastic every year for material recycling. It's the same as 5,000 tons of crude oil. The cages contain 7 different sorts of waste. The cages are emptied automatically when they're full. The material is then pressed into cubes for recycling, each containing about 1 meter squared. PET, PE, PP, foil, mixed plastic, mixed paper, non-magnetic metal. The remaining waste is sent to incineration. The energy will be used for heating and electricity. The green bags of food waste will be brought to a biogas plant after sorting, where it will be transformed to biogas and biofertilizer, giving both environmentally friendly fuel and fertilizer for food production. Our waste trucks are now using your banana peel, your coffee grounds, and your apple cores for fuel. The circle of recycling is complete.
Okay. So if I go back, I'm trying now to come towards the end. So this means that this is an example of one such central sorting facility in Norway aiming at both separating out organic food for biogas, but mainly aiming at separating different fractions of plastic waste. And given that facility, they had during the last few years a sorting efficiency of, let's say, around 35–40%. There are 2 such facilities in Norway in large cities, and there is also one on the planning stage for Trondheim. But despite the use of such advanced technologies, as you understand, there are opportunities, but there are also constraints. They cannot manage to sort out more than some 40% of the waste. And then you have, of course, agricultural waste in addition. So another challenge that we have is that the plastics, when introducing bioplastics, it's not straightforward to have the bioplastics combined with fossil plastics, because as also Katarina said in her introduction, the bioplastics have a different character chemically, and therefore they are kind of contaminating the flows of regular plastics or fossil plastics in the recycling schemes. Therefore, one of the aims has been to try to develop biological plastics that is degradable. Being degradable means that they are expected to meet the specifications of an international standard, the EN 13432, which means basically that more than 90% of the plastics should be degraded and with a weight loss during some 6 months if you are using thermophilic composting. So there are opportunities, of course, with several opportunities and advantages in bioplastics, but there are also difficulties. Is that biodegradable plastics really degradable? These are the formal requirements. And when you look at tests, there is not very much literature on that internationally, but there are some experiments. So on thermophilic composting, you can see that this is cellulose paper and so on, but the plastics are down here. Fossil plastics is very low, it's close to zero. So obviously thermophilic composting means that if you are successful in bioplastics to be biodegradable, it will have to come very low under the thermophilic composting. However, this is uncertain in practice. Natural environment have a very different condition. It's far from thermophilic industrial composting. Large variations in polymer chemistry exist, and not many studies are done in order to verify these things. And these are results if you incubate plastics in soil. So you can see different kinds of plastics here, PP, polystyrene, PET, and so on, and they are far from at a high level and very far from 90%. So the cumulative percentage of carbon lost, meaning weight loss, basically. So they are far from meeting the standard. And this is fermentation. So this means that under certain industrial, let's say, controlled conditions, it is very difficult to have the common types of plastic today, even also some bioplastics successfully being degraded. One more challenge is, of course, the complexity of our systems. This is a super high quality research article by Zhang et al. From California, Chemical Reviews in 2018, telling about the challenges in technology development and innovation research and innovation work in industry. So you see the value chain from resource extraction, the production of feedstock to monomers, to polymers, and then to products. And then these products are used in society. And when they become waste, what do you do with them? You would try to have even a product back from product to polymer recycling, or back to chemical recycling to monomers, or feedstock recycling, and so on. So there are different opportunities for innovations here. You have on the production side, ILP 1, 2, and 3, new technologies for large-scale economic production and making platform chemicals and polymers and recyclable bioplastics. And you also, of course, have on the waste management side, innovation potentials for new technologies for plastic recycling back to monomers and feedstock. However, the conclusion from this study is that innovations that give technical and economical attractive improvements are needed at all stages of the life cycle, all stages. Different types of bioplastics require also different types of innovation. So there is no straight, simple fix to that challenge from a, let's say, plastics polymer chemistry point of view. So therefore, which polymer types actually could succeed in future? Here you see a classification diagram of plastics according to the degree of renewability and the degree of recyclability. And of course, you would like to be up here with a high renewability and a high degradability. However, is a sorting of different plastic polymers, depending on how it is renewable or biodegradable. You wouldn't like to be here, but here you see several of the types that we know today. And this would be good, but then of course it's not degradable. So if you're here, you would have to be sure that you are in countries with a well-developed infrastructure for take-back systems and recycling schemes. So in the future, we have to look for polymers that are here, where we are not that vulnerable on the functioning and the completeness of recycling systems from a technological and industrial point of view, because we have polymer types that actually can handle these things. So you should look really at this literature. That study examined more than 500 research studies and gave a very good description of the challenges in plastic waste. So that was my time. It's 10 o'clock, so I think we have to end. I would just conclude by saying that after have been working in this area for some years, I can say we do have the methods in order to examine and understand, but there is a large bulk of research work that is needed to be done with students and young researchers involved. There are super many opportunities to follow, but each of those opportunities is not necessarily straightforward to being implemented. So it means that there are challenges in this area. And hopefully during the next 5-10 years, we will find solutions in practice also for many of these things and transform them into industrial, let's say, and societal successful schemes. So thanks a lot.